So my name is Stephen Bates. I am the Chief Technology Officer of a startup called Adedicom. We are doing something called NVMe, NVM Express computational storage. And today I want to talk about how we can accelerate computation and computational storage in systems that are based on RISC V processors. So a quick little piece of mathematics. RISC V plus Adedicom plus NVM Express equals awesome. And I am going to spend the rest of this talk trying to justify why that is the case. First, I'm going to talk about what RISC V is. Ha, that's a joke. You wouldn't be here unless you already knew more about RISC V than I probably do. I am going to talk a little about something called NVM Express. It's 4 in the afternoon. I'm sure everyone's tired. But a quick show of hands. Have you heard of NVM Express? Hands up if you have. Hands up if you know if you have an NVM Express device in your laptop or handheld or whatever. Great. OK, good. That's good. So I'm going to talk a little about NVM Express. I'm going to talk about NVMe performance on a Linux-capable RISC V SoC, actually one from Sci-Fi. And I'm going to show you how NVMe has a lot of potential, but in the current SoC incarnations, it actually sucks. And I'm going to talk a little about why it sucks. And I'm going to talk a little about some of the things we could do to make it suck a little less. I'm going to introduce something called NVMe computation. This is a kind of an area of active development and standardization right now. I'm going to talk a little about that. And then I'm going to talk about this weird thing called peer-to-peer DMAs, P2P DMA. And I'm going to talk about work that we've been doing in the Linux kernel to enable that for a variety of architectures, including, hooray, RISC V. And then I'm going to finish off with some examples of what happens when you bring all this stuff together and show essentially how we're moving to a paradigm where you don't necessarily need to have an Intel Xeon in your system to get a lot of work done. Heterogeneous computing and changes in computer architecture and challenges with Dennard scaling and Moore's law are kind of pushing us towards a more heterogeneous, let's have a bunch of high-speed devices communicating directly with each other under supervision of a Linux-capable device. Makes more sense. And I'm going to show you how we can actually do that today with RISC V. And going forward, things might even get a little better. What is NVMe or NVM Express? So some of you have heard of this before. What happened was there was quite a few years ago now, there was an amazing company called Fusion.io, which was bought by SanDisk, which was bought by WD, et cetera, et cetera. But what they did is they put flash on a PCIe endpoint. So they took NAND flash and they stuck it on a PCIe device, and it was shit tons fast. Like, people were used to getting data from spinning disks, and this thing was suddenly way, way faster. And everybody loved it. They're like, my applications are running faster. I'm no longer bound by I/O. And so what happened is other companies started producing PCIe solid-state drives as well. But everyone had their own fucking driver, and that's a real pain in the ass. I don't want to have to install a Micron driver because I buy a Micron drive. I don't want to install an Intel driver because I bought an Intel drive. It's a pain in the ass. So what did we do? We standardized something called NVMe, and we went to all the drive vendors and said, if you build a PCIe-attached SSD, for God's sake, make it align to the NVMe spec. And then that means we have one driver, we have one management stack, we have one way for applications to talk to it, and the world will be happy. And that's basically what happened. So NVMe is now a very successful standard. In fact, this year, I believe, is the first year where more SSDs will ship with NVMe as the interface rather than SATA and SAS combined. So we've kind of won that war. We like PCIe because it's directly attached to the processors. There are 13 million servers getting shipped this year, and 3 of them will have Gen Z as an interface, and 13 million of them will have PCIe. So I think it's a very successful protocol, and NVMe builds on top of that. We've even extended it so we can now communicate NVMe commands over something like Ethernet, over RDMA and TCP/IP. So I can have a client that thinks it's talking to a local drive, encapsulate that over an Ethernet network, and have it have an action on a remote device. That's called NVMe over Fabrics, and I'll talk a little bit about that at the end of the talk. Superb support in Linux. Everyone out here who's building an accelerator, you will have to hire someone who is a PCIe driver, and you will have to upstream that driver so your customers can take advantage of your wonderful accelerator. I don't have to do that. My startup is aligned to NVMe. I get some of the best kernel developers on the planet writing my driver for me, and I don't even have to pay them. And they're doing it for VMware, and they're doing it for Windows. So my little tip of the day is if you're doing a PCIe RISC V accelerator, think about doing NVMe, and you'll save yourself a driver developer or 5. There's a healthy roadmap of upcoming features, low latency, so we have devices that are based on something that's not NAND, which means it's AND, Boolean joke, boom. Sorry, oh God, everyone's asleep today. Computational storage, so not just storing data, but perhaps doing mathematical functions on that data while it's on the NAND. That's something that we're working on. Things like I/O quality sources. You can go to the nvmexpress.org website. You can download the spec. It's an open standard. It's very like RISC V. You can be a member company. You can have voting rights. Everything ends up in the public domain. And so there's a lot of similarity between RISC V as a political entity and NVM Express. There's a lot of different form factors for NVMe. They are also standardized. There's a lot of performance features that are great, multiple hardware queues. And there's a really good management stack. And that's important. If I want to go and deploy 10,000 accelerators in my data center, I need to manage those. I need to know when they fail, how to make LEDs change color so IT operators can go in and switch them out and replace them with new accelerators. People like Facebook and Amazon care about manageability at scale. And NVMe has a really good management stack. And that's important. If I take an NVMe drive, which is capable of doing quite a few gigabytes per second of I/O, and I plug it into a RISC V SoC, the performance is shit. In fact, as we try to increase the performance, we find that we saturate at about 200 megabytes per second. So this was using a very recent version of the Linux kernel. This was using the Freedom SoC card from Sci-Fi. And try as I might, even though the SSD is more than capable of generating much more data than this, I could not get anything more than this 200 megabytes per second using the unleashed expansion card and with all the PCIe stuff. And it wasn't just a case of PCIe bandwidth. There's some other stuff that was going on that we found was rather interesting and rather challenging. So NVMe is designed to be pretty performant, and it is designed to be architecture agnostic. But there are a couple of things happening on the RISC V SoC that were causing problems. One of them is it doesn't have the widest DDR controller on the planet. So it had some limitations in terms of how much of this DMA traffic can it pump out to the DRAM buffers that are allocated for those DMAs. The PCIe bandwidth is a problem. There is some Gen 2 on that expansion card. So Gen 2 is a few hundred megabytes per second per lane. It's not the bottleneck, but it's probably contributing. The CPU cores are, for want of a better word, wimpy. So it takes them a certain amount of time to issue an NVMe command, basically do a DMA. And there's only so many of those per second it can do. And so the CPU is actually working quite hard in order to get the DMA. There's a couple of others that I've highlighted in red that are interesting because they're actually based on things that we might do something about in the future. The virtual memory layout for RISC V, and not just for the Sci-Fi, but for RISC V in general, is really, really bad. Some of the choices that have been made around where the linear space sits versus where the virtual mapping starts is not great, especially when you have a 32-bit root port on a 64-bit device. Another challenge is that we don't have an I/O MMU, obviously, in these SoCs yet. So if you want a DMA to an address that's above 4 gig, but you only have a 32-bit root port in your PCIe, you physically have to bounce buffer through memory. And we have something in Linux called the software IOTLB to do that. But that's basically mem copies. And mem copies are incredibly prohibitively expensive on an SoC because you're basically doing load, 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 store, 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 store. So all of these things contribute to the performance, and we ended up at about 200 megabytes per second. So having really good PCIe is one thing. Having it actually work is another. And there's things we need to dig into to make that better. All right. So that was doing a traditional DMA. So we were asking the NVMe drive to copy some data from the drive and put it in physical memory DDR connected to the SoC. That is the traditionally, until the latest Linux kernel, until 4.20, That has always been the path a DMA must take. When you do a DMA in Linux, if you try to do anything else in any kernel prior to 420, you would get an error code if you tried to do it. What we've done in the 4.20 kernel is introduce a new framework that we call P2P DMA. And this is upstream. 4.20 is still in the RC cycles, but as soon as it's stamped, it will all be up there. And it's already in the RC, so you can go play with it right now. And what we do is we actually enable a new path for DMAs where you can pass in an I/O memory address and not have the DMA layer reject it. So you can actually pass in a PCIe bar as the destination for a DMA. Now, why is that interesting? It's interesting because now I can actually move data directly from one PCIe endpoint to another without having to bounce through system memory and hit some of those performance limitations I mentioned on the previous slide. That's great. Another interesting thing is that in NVMe, we actually have a standard, an optional standard for exposing a bar in a way that we present some of the attributes of that bar to the operating system so it understands its capabilities. We call that a controller memory buffer. And NVMe drives are starting to appear on the market for a variety of reasons with these controller memory buffers. And surprise, surprise, our product has a very good CMB, and we leverage that. Because now I can actually do DMAs directly between my endpoints. And it's worth noting what we've done in the Linux kernel is not NVMe specific. Any PCIe driver at all can, if it wants to, choose to play in the DMA space, the peer-to-peer DMA space. So if you have a PCIe endpoint and you have a kernel, a Linux driver for that, and you want to play in this space, as of 4.20, there are some documentations in the driver device writer directory now that tell you some of the APIs that you can call in order to get your driver to play in this space. And we're working with GPU vendors and NIC vendors and FPGA accelerator card vendors in order to get their drivers updated so we can start doing more of this. And if you're interested, we can talk about it more because there are some subtleties around this that I won't have time to get into today. It's worth noting that what we've done in the 4.20 kernel only works for x86, so it only works for Intel and AMD. It is Arch-specific. We're doing some things related to what's called memory hot plug, and that's touching architecture-specific code. So it's not a case of doing it once and all architectures benefit. I'm very hopeful that some of the ARM people will do this for ARM. We've already done some proof of concept to show it can be done. And we have done it for RISC V. That's going to be what I'm showing you today. We have not chosen yet to guarantee we're going to upstream that work, but it's on GitHub so people can take it and have a look. And we may well work towards upstreaming that for RISC V because we think it's quite important, and I'll show why now. So peer-to-peer DMA lets us do pretty interesting things in terms of data movement, and NVMe computation lets us do interesting things in terms of manipulating the data that we're moving between these endpoints. Because just moving data from device A to device B is kind of boring. But if I can do a mathematical function on that data in one of those endpoints, it gets a lot more interesting. So NVMe computational storage involves taking these NVMe SSDs and adding some standards-based way of doing data manipulation on them. So this is leveraging the fact that NVMe is a great protocol for PCIe accelerators. The endpoints don't have to be SSDs. They just have to have NVMe as the protocol by which you communicate with them. So it could be a smart NIC that presents as an NVMe SSD. There's a little company called Annapurna that got bought by Amazon for exactly that reason. That's what they were doing. And Amazon loved it, and they use it in AWS today. We can leverage all the goodness of the NVMe ecosystem and still get to connect accelerators to the host processor. And the great thing is it doesn't matter if that host processor is RISC V, if it's ARM, if it's Intel, if it's AMD, if it's Power. They all have an NVMe driver, right? Linux has a really, really good NVMe support. Part of what we're doing right now as a startup is proprietary. It's not standard. But as of 2 weeks ago, the SNIA, which is the Storage and Networking Industry Association, has set up a technical working group to start standardizing this. So what I'm hoping is in a year or two from now, NVMe drives, as well as advertising their capacity, will also have a standards vendor-neutral based way of saying, and I can do these computational services. And those services could be fixed functions like compression, or it could be saying, I can run a Docker container. I can run a Berkeley packet filter. I can do any kind of thing. These are the companies that are involved in that standardization effort. You can see there's some reasonably large names there, and there's also some startups. And more companies have even joined since I put this slide together. So what does that mean for RISC V? I think one of the things I want to talk about, one of the things I'd like to make kind of clear today is that using this paradigm of peer-to-peer and NVMe computation, we can actually decouple the performance of the CPU from the performance of the I/O path. I can do pretty amazing things in terms of the amount of gigabytes per second I can do down at the PCIe level without having to have a Xeon or an EPYC or some other huge processor managing it all. I can actually get away with using a very small RISC V core. So we have a demo at the SciVive booth, and I suggest you come and see it because that probably explains things much better than I can in a slide. But what we can do is we can take the SciVive SoC, we can connect that to a microsemi switch. We're actually using a Gen 4 switch, one of their early Gen 4 samples they gave to us. And we can do Gen 4 PCIe traffic that's managed by this small RISC V SoC. But all the DMA traffic is done through the peer-to-peer DMA framework and never goes above the switch. So I've completely decoupled the performance of my data plane from my control plane. My control plane can be totally wimpy. It can be a $10 SoC, and yet I can be doing multiple gigabytes of data movement and manipulation and storage and networking down below this Gen 4 switch. We were doing, in the demo we have over there, we're doing about 5 gigabytes per second of zlib compression. So we're compressing data at a rate of 5 gigabytes per second, and we're doing that using the RISC V Freedom SoC as the control plane manager. We don't have it in the demo today, but we can add things like RDMA network cards to that, and we can start doing things like NVMe over fabrics. We can start pulling in data from the network or pushing results out across the network, and we can start scaling all of this up. We still have Linux managing everything. If there's a problem, if there's an error event, Linux can come in and step in and try to tidy everything up. But our data plane is now completely decoupled from that. Come see the demo. Much better to see it in person. So I will promise to be over at the SciVive booth after the talks have ended today for a little bit at least, and I can walk people through the demo if they're interested. Basically, we're doing 5 gigabytes per second. If we do the math on that, we're about 1,500 times more efficient than using the actual RISC V core to do zlib compression. So we're quite a bit more efficient. And obviously, there's a price and the power thing that has to be factored in, but I think it's still going to be 100-fold more efficient to use our device than to use those RISC V cores to do it. And we're totally scalable in the sense that because we're all below the switch, you can just add more of us and more of the NVMe drives and things scale up. We did a very similar demo to this at Supercompute with an AMD system and got very, very large amounts of performance using a similar approach. Okay. I think the key thing I'd like people to take away is that bullet point at the bottom right-hand side of the slide. The I/O is at PCIe Gen 4. The CPU is at PCIe Gen 2. I've completely decoupled the performance of the processor from the performance that I'm getting out of the system. And I think that's very interesting. So just to talk about conclusions and future work, Linux on RISC V is a fantastic platform for PCIe and for NVM Express. It's open hardware, allows innovation. Linux has great NVMe support for any architecture. And the RISC V lets us do things like look at root ports, host bridges, and start playing around with IOMMUs. There are some issues with incarnations as they stand today. Some of these are just because the SoCs are still very wimpy. We don't have multiple memory bandwidth. We don't have big PCIEs. Some of it are choices that we're making in the software stack. We may want to revisit how Linux does its virtual memory mapping for RISC V. Peer-to-peer has no performance bottlenecks because the DMAs never actually go near the RISC V. We can do some very interesting things with that. One of the things that we want to do next is RDMA NICs and do some of this in a scale-out fashion across Ethernet networks. All the code that I talked about today, all the peer-to-peer DMA stuff, are ports for RISC V. The QEMU models we do just some of the emulation work before we play with hardware. The root FSs that we installed on real hardware, all of that is available on GitHub. Take a picture of this slide or come talk to me and you can go download it from GitHub. So anyway, if you're interested in peer-to-peer, if you're interested in doing very high-performance stuff with wimpy cores, which I think is a very interesting computer architecture model as we move into the world of heterogeneous compute, then take a look at some of this. If you're working on accelerators based on RISC V and their PCI, maybe take a look at the NVMe computation standardization stuff. It might save you a lot of trouble to align to that spec, so you don't have to do a lot of your own development work. And if you're interested in seeing what we can do, come and see me at the Sci-Fi booth maybe a little after the next talk or when we finish for the day.